January 17th, 1991. 2:51 a.m. Baghdad. A 2,000-pound laser-guided bomb detonates directly inside the ventilation shaft of the Iraqi Air Defense Headquarters. The explosion does not blow outward. It drives downward, channeled through the concrete like a fist through paper, vaporizing the command nerve center of the most sophisticated Soviet-designed air defense network outside the Warsaw Pact. 30 seconds later, a second bomb obliterates the primary telecommunications exchange, feeding the entire northern missile battery grid. Then a third. Then a fourth. 17 precision strikes in the opening 6 minutes, each one surgical, each one catastrophic, and not a single radar screen in the entire city showed a single aircraft in the sky. 6,000. Remember that number. That is how many surface-to-air missiles the Iraqi Air Defense Network fired at American aircraft over the next 43 days. And here is the number that ended an empire. 0. Not one F-117. Nighthawk was touched, not scratched, not forced to divert. A fleet of 42 aircraft representing just 2.5% of the entire Allied Air Force destroyed 40% of Iraq's complete strategic target list. They did it invisibly. They did it with impunity. And the men who built them started with nothing but a rejected physics paper from a Moscow library that the Soviet Union itself had thrown in the trash. But that story begins not in Nevada and not in Baghdad. It begins with a man named Dennis Overholser, a radar engineer with ink-stained fingers and a habit of reading academic journals that everyone else ignored, who in 1974 found an equation buried in a translated Soviet technical paper that made him go completely still at his desk. He did not move for a long time, because what he was reading, if it was true, meant that everything the American military believed about aircraft design was wrong, and everything the Soviet Union had spent 40 years building to protect itself could be made irrelevant by a shape that looked less like an airplane and more like a piece of broken glass. To understand what Overholser discovered, you need to understand what the world looked like in 1973. That year, during the Yom Kippur War in the Middle East, Soviet-supplied SA-6 gainful missiles tore apart the Israeli Air Force in ways that sent shockwaves from Tel Aviv directly to the Pentagon. In 18 days of fighting, the Israelis lost over 100 aircraft. Their best pilots, flying their best American-built jets, were being killed by missiles they could barely detect before impact. The SA-6 used a mobile radar system that was nearly impossible to locate and destroy before it fired. The lesson was blunt and brutal. The era of conventional air power was over. The skies above any future battlefield defended by Soviet air defense doctrine would be a killing field, and the Americans had no answer. The Pentagon convened emergency reviews. The conclusion was unanimous and terrifying. Any conventional strike aircraft, any B-52, any F-111, any fighter bomber flying into a Soviet integrated air defense network would be destroyed. The math was merciless. Radar cross-section, the measure of how visible an aircraft is to radar, determined survivability more than speed, more than altitude, more than jamming. A B-52 had the radar signature of a flying warehouse. Even the nimble F-15, the most advanced American fighter of the era, showed up on Soviet radar like a bright moving billboard. The wall was real, and America had nothing that could breach it. DARPA issued a classified request in 1974 that amounted to a single desperate question. Can we build an aircraft that radar cannot see? The request went to every major aerospace contractor. Most of them responded with polite, technically sophisticated explanations of why the answer was no. Radar waves hit physical objects and bounce back. You could reduce the return. You could use electronic jamming. But you could not make a flying machine invisible. It was a physical law. The best minds in the industry said so. The problem was impossible. And they were right, using every design principle that had governed aviation since the Wright brothers. But Overholser was not an aerodynamicist. He was a radar specialist working at Lockheed's Advanced Development Projects Division, a secretive Burbank facility known as the Skunk Works, a place that had built the U-2 spy plane, and the SR-71 Blackbird, a place where impossible problems were the only kind they accepted. And in 1974, while doing background research on electromagnetic scattering, he found a paper published in 1962 by a Soviet physicist named Pyotr Ufimtsev titled Method of Edge Waves in the Physical Theory of Diffraction. The paper had been published openly. Ufimtsev's own supervisors had read it and concluded it had no practical military value. They never classified it. It was translated into English and distributed through academic channels, sitting in plain sight for over a decade, waiting for someone to understand what it actually meant. What it meant was everything. Ufimtsev's equations proved something that overturned the foundation of aircraft design. The radar reflection of an object is not determined by the size of the object. It is determined by the geometry of its edges. A smooth, curved fuselage, the shape of every aircraft ever built, acted like a curved mirror. Radar waves struck it and scattered in thousands of directions, with a significant portion reflecting directly back to the radar receiver. That was why aircraft showed up so clearly on radar screens. But Ufimtsev's math revealed a different possibility. A shape built entirely from flat-angled triangular panels, like a faceted gemstone, would behave like a shattered mirror. Each flat panel would deflect radar energy away from the receiver in a single narrow, useless beam. Angled precisely, such a shape would produce a radar cross-section not of a barn, not of a bird, but of a steel marble, or smaller. Overholser grabbed a computer specialist named Bill Schroeder, and together they translated Ufimtsev's equations into a software program they called Echo 1. They used it to design a shape. What the program produced was genuinely grotesque. It was a pyramid of sharp, flat triangular panels meeting at hard, unforgiving angles. It looked like something folded from paper by a child who had never seen an airplane. There were no curves, no smooth transitions, no concession whatsoever to the principles of aerodynamic flow that every engineer in the world treated as sacred law. The Skunk Works team looked at it and gave it a name that captured exactly what they thought of its chances. They called it the Hopeless Diamond. They built a wooden mock-up. They mounted it on a pole in an open field. They pointed a radar at it. The operator running the radar equipment looked at his screen, then looked at the pole, then looked at his screen again. He assumed his equipment had malfunctioned. There was nothing there. The return was essentially non-existent. The Hopeless Diamond had a radar cross-section 1,000 times smaller than any aircraft in the history of flight. They had mathematically proven that invisibility was achievable. The problem was that they had designed something that could never leave the ground. By every known law of aerodynamics, the Hopeless Diamond was a death trap. The flat panels and hard angles that made it radar invisible also made smooth airflow across its surfaces a physical impossibility. Conventional aerodynamic stability depends on curved surfaces, allowing air to pass over them in predictable controlled patterns. The Hopeless Diamond had none of that. An aerodynamics team ran the numbers and delivered their verdict without hesitation. This shape would tumble out of the sky the instant it was released. It could not glide, could not maintain level flight, could not be controlled by any human pilot through any conventional control system. It was aerodynamically suicidal. Multiple senior engineers inside the Skunk Works told Ben Rich, the program director who had inherited the organization from the legendary Kelly Johnson, that the entire concept should be abandoned immediately. Rich did not abandon it, because at precisely this moment, something was happening 30 miles away that changed the equation entirely. The United States Air Force was testing an experimental variant of the F-16 fighter built around a concept called fly-by-wire. In this aircraft, there was no mechanical linkage between the pilot's control stick and the aircraft's control surfaces. When the pilot moved the stick, the input did not go to a cable connected to a flap. It went to a computer. The computer processed the input and sent electrical signals to the control surfaces. The computer flew the plane. The pilot aimed it. The Air Force had built this system to handle aircraft that were slightly aerodynamically unstable designs that traded some passive stability for increased maneuverability. But Ben Rich and the Skunk Works team saw something in that technology that the Air Force had not yet imagined. What if you did not use the computer to manage slight instability? What if you used it to manage total catastrophic permanent instability? What if the computer made not occasional corrections, but thousands of micro-adjustments, every single second, catching the airframe every time it lurched, rebalancing it, correcting it, tricking it into maintaining controlled flight, when by all physics, it should be tumbling into the earth? The pilot would not fly the aircraft. The pilot would simply tell the computers a direction. The computers would handle the impossible work of keeping a shape airborne that had no right to be there. The hopeless diamond would not need to obey the laws of aerodynamics. It only needed a digital brain fast enough to cheat them fast enough and smart enough to compensate for every deviation thousands of times per second with no delay, no hesitation, and no margin for error. In 1974, the computing technology to do this barely existed. The microprocessor had only been invented 3 years earlier. The idea of a quadruple redundant digital flight control system powerful enough to stabilize a fundamentally unflyable aircraft was insane by every practical standard of the era. Every program manager who heard the full proposal said the same thing. You are describing something that cannot be built. Ben Rich looked at Ufimtsev's equations, looked at the Echo 1 simulations, looked at the fly-by-wire data, and authorized the program anyway under the codename Have Blue. They had the invisible shape. They had the theoretical computer architecture to make it fly. What they did not yet have was any proof that both ideas could be fused into a single aircraft that a human pilot could actually survive. The testing that was about to begin in the Nevada desert would be the most secretive aviation program in American history. And it would end with a result that no one, not even the men who built it, could have fully predicted. In Part 2, we go behind the fence at Groom Lake, where the pilots who flew the Hopeless Diamond described the experience as fighting a machine that was actively trying to kill them every second they were in the air. In Part 1, we watched a radar engineer named Dennis Overholzer find a discarded Soviet physics paper and use its equations to design a shape that made radar operators think their equipment had broken. The Hopeless Diamond had a radar cross-section 1,000 times smaller than any aircraft ever built. The problem was that it could not fly. And the solution, a quadruple redundant digital flight computer system powerful enough to tame an aerodynamically suicidal airframe, existed only in theory. Ben Rich had authorized the program. The code name was Have Blue. And now, the hardest part was not the engineering. The hardest part was the United States Air Force itself. In 1975, the American military establishment was an institution in psychological recovery. Vietnam had shattered its confidence in unconventional thinking. The generals and program managers who controlled the defense budget had learned one lesson from that war above all others. Never again gamble institutional resources on unproven concepts from engineers who had never commanded men in combat. The culture of the Pentagon Acquisitions Office was built on precedent, on incremental improvement, on programs that could be measured, tested, and justified in quarterly reports to congressional oversight committees. Into this environment, Ben Rich walked with a proposal to build an aircraft that looked like a broken paper pyramid, could not be flown by human hands alone, and whose entire theoretical foundation rested on the work of a Soviet academic whose own government had dismissed him as irrelevant. The first formal briefing with the Air Force Program Office in Washington lasted 45 minutes. The general presiding a decorated Vietnam-era aviator named Harold Pugh, who had flown over 300 combat sorties and knew air power doctrine. The way a priest knows scripture, listened to the entire presentation without interrupting. When Overholzer finished and the slide projector went dark, Pugh leaned back in his chair and said 4 words. "This is not serious." He was not being dismissive for political reasons. He genuinely believed, based on 30 years of aviation experience, that the concept was physically incoherent. You cannot build a combat aircraft around a shape that no aerodynamicist on Earth will certify as flyable. That is not innovation. That is waste. Rich pushed back. General, the radar data is not theoretical. We built the model. We tested it. The return is real. Pugh folded his hands on the table. Mr. Rich, I have seen promising radar test results before. I have also seen promising radar test results turn into programs that killed pilots and consumed $3 billion. Come back when you have something that flies. The meeting ended. Rich walked out into the Washington afternoon with the program effectively dead. And that is when everything should have stopped. Except that 3 weeks later, a phone call came from a man most people inside the Pentagon had never heard of, a quietly influential Air Force colonel named William Olone, who ran a small advanced concepts office, buried so deep in the organizational chart that most generals forgot it existed. Olone had seen the Have Blue presentation notes. He wanted a private meeting, no documentation, no official attendance record. Olone was not a dreamer. He was a systems analyst who had spent the previous 5 years studying the operational mathematics of the Soviet PVO air defense network in exhaustive detail. He had modeled every radar frequency, every missile engagement envelope, every tracking algorithm in the Soviet integrated system. And his conclusion, which he had been unable to get anyone to take seriously for 3 years, was that the entire American strike doctrine was mathematically broken. Against a fully operational Soviet air defense network, the projected loss rate for conventional strike aircraft was not 5% per mission. It was closer to 30%. In a sustained air campaign against the Soviet Union, America would run out of aircraft and pilots within weeks. Olone understood exactly what Overholser's equations meant in operational terms. They meant survival. He told Rich he would secure a formal demonstration trial with a senior review panel. 1 test. Controlled conditions. 6 months to prepare. If the demonstration failed, the program would be canceled permanently and no further appeals would be entertained. If it succeeded, Olone would personally carry the results to the Deputy Secretary of Defense. Rich accepted without hesitation. The 6 months that followed were the most pressurized period in the history of the Skunk Works program. The team working at the classified Burbank facility was small by institutional standards, fewer than 50 engineers and technicians. They were working without the support structures that conventional defense programs enjoyed. No dedicated wind tunnel time, no formal materials testing laboratory, no production supply chain. The first full-scale Have Blue airframe was being assembled from components sourced through deliberately fragmented procurement channels to prevent any single contractor from understanding what they were building. The fly-by-wire computer system sourced from the F-16 experimental program had to be recalibrated from the ground up for an airframe whose instability parameters were unlike anything the software had ever encountered. 3 times during integration testing, the computer system crashed during simulation runs, at the moment the virtual airframe exceeded its instability threshold. 3 times the software team worked through consecutive nights to rewrite the compensation algorithms. The 4th run held. Barely. The morning of the demonstration was November 4, 1977, at a dry lakebed test facility in the Nevada desert. The temperature at dawn was 31 degrees Fahrenheit. Frost covered the hardpan. 7 Air Force officers from the review panel sat in folding chairs behind a painted line 100 meters from the runway threshold. General Pugh was not among them. He had sent a deputy, a colonel named Marsh, who had been briefed to watch the demonstration and report back. Marsh arrived with the body language of a man who expected to file a short negative report by early afternoon and return to Washington in time for dinner. The Have Blue prototype was rolled out of its temporary hangar at 06:15. It looked wrong in the gray morning light. There was no other word for it. Every aircraft that had ever flown looked like it belonged in the air in some fundamental way, some visual harmony between form and function that the eye recognized instinctively. The have-blue prototype had none of that. It was black and angular and deeply, profoundly strange. One of the review panel officers said quietly but audibly that it looked like something that had fallen off a larger object. The Skunk Works test pilot assigned to the demonstration, Bill Park, walked around the airframe, doing his pre-flight check with the careful, deliberate movements of a man who was not performing calm but genuinely feeling it. Park had flown the simulator for 400 hours. He knew what the computers could do. He also knew exactly what would happen if any of the 4 redundant flight control processors failed simultaneously during rotation. He climbed in without looking at the audience. The engine start sequence took 11 minutes. At 0641, the have-blue prototype began its takeoff roll. The runway at the test facility was 9,000 feet long. Park used 6,000 of them. At rotation speed, the nose lifted. The airframe immediately began its characteristic deviation, the tendency to pitch and yaw simultaneously that made every aerodynamicist who had studied its specifications shake their head. The flight computers fired. 400 microseconds of compensation. The aircraft climbed. It did not climb smoothly. It climbed in the manner of a thing that was being continuously argued back into the correct attitude by an invisible and extremely fast intelligence, but it climbed. At 500 feet, Park leveled off, turned east, and flew a clean evaluation circuit over the lake bed. The radar tracking station 3 miles from the runway had been running continuously since 0500. Its operator, a civilian contractor named Gerald Flores, who had been tracking military aircraft by radar for 19 years, was watching his scope with the focused attention of a man who knew that his data was the entire point of the exercise. He watched the have-blue take off. He tracked it through the turn, and then, at a distance of approximately 2 miles, he reported what he saw to the review panel observer over the open radio channel. His exact words recorded in the official test log were, "I have rotation and climb on optical. Radar return is negligible. Repeat, negligible. I am looking at an aircraft in flight and my radar does not believe it is there." The review panel Colonel Marsh stood up from his chair. He did not say anything for several seconds. The have-blue completed its circuit and landed. Park taxied back to the line and shut down the engines. The radar tracking data was pulled immediately. The have-blue prototype's measured radar cross-section during flight was 0.001 square meters. A conventional fighter aircraft of comparable size produced a return of between 1 and 5 square meters. The have-blue was not slightly harder to see. It was between 1,000 and 5,000 times less visible than anything in the current American inventory. Marsh walked to the communications station and requested a secure line to Washington. The production authorization for what would become the F-117 Nighthawk program, redesignated Senior Trend, was issued within 60 days of the November 1977 demonstration. The official USAF commitment included funding for 20 development aircraft and an initial operational fleet of 59. Groom Lake, the isolated facility in the Nevada desert known to its inhabitants as the Ranch, was expanded to accommodate the program. The pilots selected for the unit were told they were joining a classified test program. They were not told what they would be flying. When they saw the F-117 for the first time, the reaction was consistent across every pilot who experienced it. Disbelief followed immediately by the professional reflex to climb in and find out what it could do. The disbelief of the pilots was minor compared to the institutional resistance that erupted when word of the program's existence began to filter in carefully controlled fragments through Air Force Operational Command. Unit commanders, who were told their strike missions would be augmented by this new classified platform, reacted with suspicion, verging on hostility. "You are telling me," one wing commander said during a closed briefing in 1980, "that I am supposed to trust the most sensitive targets on my list to an aircraft that my radar operators cannot track, that flies only at night, that has no gun, no air-to-air missile capability, and that looks like something a child built from construction paper. That is what you are telling me." "Yes," the briefer replied. "That is exactly what we are telling you." The early operational crews who flew the F-117 out of Tonopah Test Range in Nevada from 1983 onward lived a classified existence of extraordinary discipline. They flew exclusively between last light and first light. They commuted to work on unmarked charter flights from a public terminal in Las Vegas. Their personnel records listed them as attached to non-flying administrative units. Their families knew they flew aircraft but were told nothing more. For 8 years, from the first operational flight in 1983 to the morning of January 17, 1991, the F-117 did not officially exist. And in Moscow, the GRU Intelligence Directorate was picking up fragments of something. Ghost signals on border radar installations, pilot reports of anomalous returns over the Barents Sea, a Siberian radar operator who filed a report about a black spot moving across his scope 3 nights in a row and was reprimanded for it. The Soviets knew something was out there. They could feel it the way you feel a presence in a dark room before you hear it. But they could not see it, could not name it, could not track it. Their entire intelligence apparatus was chasing a phantom that was being built, tested, and perfected in a desert they had no access to. And in Part 3, we will watch what happened when the Soviets finally got their hands on the one piece of evidence that confirmed their worst fears and discovered that the technological gap between them and America was not a gap at all. It was a cliff, and they were already falling. In Part 1, a radar engineer named Dennis Overholzer found a discarded Soviet physics paper and designed a shape that disappeared from radar screens. In Part 2, that shape survived institutional resistance, passed a live demonstration that silenced a room full of skeptical Air Force officers, and became the most classified aviation program in American history. For 8 years, the F-117 Nighthawk flew only at night, operated from a base that officially did not exist, and accumulated over 10,000 flight hours without the world knowing it was airborne. Then, in November 1988, the Pentagon held a press conference. They showed one photograph. And in Moscow, the reaction was not what Washington expected. It was worse. Because the Soviets did not just see an enemy aircraft. They saw the reflection of their own failure staring back at them. And now this was no longer a technology demonstration. This was a weapon pointed at the heart of everything they had built. The photograph released by the Pentagon on November 10, 1988, showed a black, angular, deeply alien-looking aircraft on a tarmac in blinding Nevada sunlight. Assistant Secretary of Defense Daniel Howard read a prepared statement confirming that the United States Air Force had developed and fielded a stealth aircraft designated the F-117A. The statement was 4 sentences long. The photograph was grainy and taken from a deliberately unhelpful angle. Howard took no questions. The entire press conference lasted less than 8 minutes. In Washington, the reaction was measured curiosity. In Moscow, a team of GRU analysts pinned the photograph to a board in a secure room and did not speak for almost a minute. Then they pulled Ufimtsev's 1962 paper from the archives. They laid his equations next to the image on the board. The match was immediate and exact. The faceted geometry of the airframe, the hard angular edges, the flattened planform. Every design choice visible in the photograph corresponded precisely to the theoretical framework their own physicist had published 26 years earlier, and which their own military establishment had dismissed as academically interesting but militarily useless. The shock in that room was not the shock of confronting the unknown. It was the specific nauseating shock of recognizing that you had held the answer in your hands, decided it was worthless, and watched your enemy pick it up and build the future with it. The GRU Commission filed its assessment within 72 hours. The conclusions were stark. The F-117 was real operational and deployed in unknown numbers. Its radar cross-section, based on the Ufimtsev geometry visible in the photograph, was estimated at between 0.001 and 0.003 square meters. For context, the SA-2 missile guidance radar, the backbone of Soviet exported air defense doctrine, required a minimum target return of approximately 2.0 square meters to achieve reliable tracking and engagement. The F-117 produced a return 1,000 times below that threshold. Every surface-to-air missile system the Soviet Union had deployed, exported, or was currently developing was functionally blind to this aircraft. The Commission recommended emergency acceleration of 3 counter-programs simultaneously: low-frequency meter-wave radar modernization, passive infrared detection array development, and acoustic sensor network deployment along likely ingress corridors. The Politburo approved all 3 within a week. The budget allocations were enormous, and every single program failed to produce a viable counter before January 17, 1991. The low-frequency radar work produced the most promising theoretical results and the most operationally useless practical outcomes. The P-18 spoon rest meter wave system could indeed detect a disturbance in its coverage area when the F-117 passed through, but what it produced was not a track. It was a probability zone. A 50-kilometer-wide region of sky where something might be present moving in an uncertain direction at an uncertain altitude and speed. You cannot fire a missile at a probability zone. The missile guidance systems that existed used centimeter-band fire control radars, and the instant those radars illuminated the F-117, its facets deflected the beam away from the receiver, and the aircraft vanished from the scope. The Soviets were trapped in a physics loop they could not exit. Their detection radar could feel the ghost. Their kill radar could not see it. And without a continuous track from detection through engagement, every missile in their inventory was useless. The infrared passive detection program ran directly into the F-117's exhaust suppression system. The aircraft's engines vented through long, flattened exhaust slots that mixed hot gas with ambient cold air before it left the airframe, reducing the thermal plume to a temperature only marginally above background. The acoustic program was abandoned after testing revealed that the F-117's General Electric turbofan engines, muffled by the airframe geometry, produced a ground-level noise signature at operational altitude, indistinguishable from background atmospheric noise at distances greater than 4 kilometers. The GRU reported to the General Staff in early 1990 that no viable counter to the F-117 would be available within the following 3 years. The General Staff forwarded the assessment to Gorbachev. The implications were not discussed in writing. Then came August 1990, and Saddam Hussein's invasion of Kuwait and the construction of the largest American-led air campaign since Vietnam on the doorstep of a Soviet-equipped, Soviet-advised, Soviet-doctrine air defense network that the General Staff now knew was categorically unable to defend against the aircraft they had spent 2 years failing to counter. The Soviet military attaché in Baghdad filed reports throughout the autumn of 1990 that were read with the particular dread of people watching an accident they cannot prevent. The Kari air defense system protecting Iraq was dense, overlapping, and staffed by operators who had been trained by Soviet advisors for years. It was by any conventional measure formidable. Colonel Surov and his advisory team ran final readiness assessments in December 1990 and reported that the system was performing at 94% operational efficiency. Every radar was functional. Every missile battery was stocked and crewed. The kill zone above Baghdad was as airtight as Soviet doctrine could make it. It was not enough. It was not close to enough. And on January 17, 1991, the mathematics of that insufficiency were demonstrated with a precision that crossed from military operation into historical verdict. The opening strike package of Operation Desert Storm launched from King Khalid Air Base in Saudi Arabia at 100 local time. 10 F-117 Nighthawks flew north in complete radio silence, separated by precise time intervals, each assigned a specific set of targets inside Baghdad's integrated air defense architecture. They flew without fighter escort. They flew without jamming support. They flew at medium altitude in straight, predictable lines directly toward the most heavily defended airspace on the planet, doing something that no conventional strike aircraft had ever done against a functional air defense network. They flew as if it was not there. The target list for the first wave was built around a specific operational logic. Before anything else could be destroyed, Baghdad had to be blinded. The Kari system's command and control nodes, the sector operation centers that received radar data and coordinated missile battery responses across the entire defense network, had to be eliminated in the opening minutes before Iraqi operators could understand what was happening and switch to backup communication protocols. If even 2 or 3 sector centers survived the first wave, they could partially restore network coherence and begin queuing missile batteries using degraded but functional radar data. The timing of each strike was calculated to within seconds. At 0251, Major Gregory Feist, flying the lead F-117 of the first wave under the call sign Dark Knight, 1 released a 2,000-pound GBU-27 laser-guided bomb from 18,000 feet above the Al-Taji Sector Operations Center north of Baghdad. The weapon tracked the laser designator in the aircraft's targeting pod through 22 seconds of freefall and impacted within 3 feet of the designated aim point, which was the main ventilation intake on the roof of the hardened command facility. The explosion entered the building through the ventilation system and destroyed the interior completely while leaving the exterior structure largely intact. The radar scopes inside the building, which had been showing a clean sky, went dark permanently. Feist rolled left and accelerated toward his second target. Over the next 11 minutes, 9 additional F-117s struck the primary telecommunications relay station, feeding the northern missile battery grid, the main electrical substation, supplying backup power to the Air Defense Headquarters, 2SA, 2 battery engagement radar sites on the western approach corridor, the fiber optic junction housing that linked the southern sector radar network to the central command node and the Air Defense Headquarters building itself. 17 precision strikes, 17 direct hits. The circular error probable for the entire package, the average distance between the aim point and the actual impact point across all weapons delivered was less than 4 feet. Surov in the bunker beneath the Air Defense Headquarters watched the status board turn red sector by sector and understood with total clarity that the system he had spent his career building was not being defeated. It was being surgically removed. The attacks were not hitting random infrastructure. They were following the exact architecture of the network, destroying nodes in the precise sequence that would maximize cascading failure while minimizing the possibility of isolated sectors falling back on autonomous operation. Whatever was doing this knew the system as well as he did. It knew the redundancy pathways. It knew the backup command protocols. It was eliminating them in order. He picked up the secure line to the embassy and spoke 4 sentences to the duty officer. He said that the air defense network was under attack by an unknown platform. He said that every radar in the city was functional and detecting nothing. He said that the targeting precision was beyond anything in his operational experience. And he said that Moscow needed to know tonight that the PVO doctrine was broken. Then the line went dead. The first wave of F-117s was back on the ground in Saudi Arabia before the Iraqi anti-aircraft guns began firing blindly into the sky over Baghdad. 6,000 surface-to-air missiles were launched by Iraqi air defense units over the following 43 days of the campaign. The gunners and missile operators were not incompetent. They were firing on acoustic cues on muzzle flash reports from other units on intuition born from genuine desperation. They simply had no radar track to guide their weapons. They were shooting at a sky that their instruments told them was empty while the city burned around them. Not one F-117 was hit. Not one was damaged. Not one pilot was lost to enemy fire across 1,271 combat sorties. The 42 aircraft of the 37th Tactical Fighter Wing, representing 2.5% of the total Allied air fleet, destroyed 40% of Iraq's entire strategic target list. They eliminated the Iraqi Air Defense Command architecture on the first night. They destroyed nuclear and chemical weapons production facilities, whose locations were known only through intelligence sources, and whose hardened construction made them immune to conventional bombing. They severed communications networks that had been buried under reinforced concrete. They were the instrument that made every other component of the air campaign possible, the force that blinded the Iraqi military before the conventional strike packages arrived and removed the threat that would otherwise have destroyed dozens of aircraft and hundreds of aircrew. The Soviet General Staff received the full operational summary within 48 hours of the campaign's conclusion. They had the sortie numbers. They had the target lists. They had the bomb damage assessments. And they had Surov's final after-action report written in a windowless room in Moscow over 3 days, which concluded with a sentence that was quoted in every subsequent internal PVO review for the following decade. He wrote that the F-117 had not merely defeated the Baghdad air defense system. It had demonstrated that the concept of layered radar-guided surface-to-air missile defense, the foundational principle of Soviet air power doctrine since 1955, was permanently and categorically obsolete against an opponent possessing this technology. The Berlin Wall had fallen in 1989 and ended the Cold War politically. The F-117s over Baghdad in 1991 ended it technologically. But there is one final chapter to this story that the statistics and the battle reports do not capture. What happened to the men who built this weapon? What happened to the institution that tried to stop them? And what the ghost over Baghdad ultimately meant for the future of warfare? That story, the one that lives in the aftermath, is what Part 4 is about. Because the most important consequence of the F-117 was not what it destroyed. It was what it proved. And what it proved changed everything that came after. From a rejected Soviet physics paper found in a library to a wooden mock-up on a pole that made a radar operator think his equipment had broken to 42 black angular aircraft that flew 1,271 combat missions over the most heavily defended airspace on Earth without losing a single pilot. This is the story of how an idea that every institution said was impossible became the weapon that ended the Cold War's technological competition in a single night. In parts 1, 2, and 3, we watched the F-117 Nighthawk go from mathematical theory to combat-proven reality. But the question that the battle statistics cannot answer is the one that actually matters. What happened to the men who built it? And what did their work ultimately mean beyond the targets it destroyed? Dennis Overholzer, the radar specialist who found Ufimtsev's paper and wrote the Echo 1 program that designed the Hopeless Diamond, retired from Lockheed in the late 1980s after nearly 2 decades of classified work. He did not receive a public commendation. He did not appear on the cover of a magazine. The program he had initiated remained classified until 1988. And even after the Pentagon's press conference revealed the F-117's existence, the specific technical contributions of individual engineers remained protected under ongoing classification reviews. Overholzer went home to California. He gave occasional lectures at aerospace conferences in later years, speaking about computational methods in electromagnetic analysis with the careful, measured language of a man who had spent most of his career legally prohibited from discussing his most important work. He knew what the aircraft had done over Baghdad. He had watched the news coverage like everyone else sitting in front of a television in a house in the San Fernando Valley, seeing the bomb damage assessment footage that showed hardened command bunkers opened like tin cans, and understanding in a way that no broadcaster or military analyst could fully explain exactly how those results had been achieved. He had written the first equations. He had stared at the first radar return from the wooden model on the pole and watched the signal disappear. Whatever the institutional histories and the program citations eventually said, he had been there at the beginning in a small office in Burbank, when the future of warfare was nothing more than a number on a computer printout and a shape that looked like broken origami. Ben Rich, who had authorized the Have Blue program over the objections of multiple senior engineers and fought for its survival through years of budget reviews and institutional skepticism, lived to see the full vindication of the concept he had protected. He was present for the Gulf War coverage and spoke publicly about the F-117 program after declassification with the quiet satisfaction of a man who had known the answer to a question for 15 years before anyone else was allowed to ask it. He died in 1995, 4 years after Baghdad. His memoir, published shortly before his death, described the moment the Have Blue prototype lifted off the ground at the Nevada test facility as the most important moment in aviation since the Wright brothers. A claim that sounds like hyperbole, until you understand that what lifted off that morning was not just an aircraft, but a proof of concept that every radar system in the world was already obsolete. Rich had inherited the skunk works from Kelly Johnson, the man who built the U-2 and the SR-71, and he had used that inheritance to produce something that made even those extraordinary machines look like incremental improvements rather than genuine leaps. He understood that distinction clearly, and it gave him a particular kind of satisfaction that has nothing to do with awards or rank, and everything to do with having been right when it was expensive and professionally risky to be right. The F-117 flew operationally for 27 years, from 1983 to 2008, when it was formally retired by the United States Air Force. During that period, it flew combat missions in Panama, in 1989 in Iraq, in 1991 in Bosnia, in 1995, and in Yugoslavia in 1999. Its total operational record across those campaigns was defined by the same characteristic it had demonstrated over Baghdad: the ability to penetrate defended airspace and strike hardened targets with a precision that conventional aircraft could not match without accepting losses that commanders found unacceptable. The operational community that had initially resisted the aircraft, the wing commanders who had questioned whether a plane that could not dogfight had any place in real warfare, became its most vocal advocates after watching it perform. The aircraft that one general had dismissed as something a child built from construction paper became the most requested asset in every major air campaign for a decade and a half. The technological lineage that began with Ufimtsev's equations and Echo 1 did not end with the F-117. The B-2 Spirit bomber, which entered service in 1997, extended the faceted geometry principle into a flying wing configuration capable of carrying a much larger payload. The F-22 Raptor combined stealth shaping with supersonic performance and thrust vectoring, producing an aircraft that was both invisible to radar and capable of outmaneuvering anything it encountered. The F-35 Joint Strike Fighter, now operated by 15 nations, carries the same fundamental design philosophy into a platform built for the 21st century threat environment. Every one of these aircraft traces its conceptual origin to the decision Overholser made in 1974 to take a Soviet academic paper seriously when his own government had not. The principles that Ufimtsev published in 1962, dismissed in Moscow and ignored in Washington for a decade, now govern the design of every advanced combat aircraft being developed anywhere in the world. China's J-20, Russia's Su-57. Every nation that wants a serious military air capability now builds to the standard that a radar engineer with ink-stained fingers established in a small office in Burbank 50 years ago. The deeper lesson here is not technical. The technical achievement is extraordinary, but the more important story is about what institutional systems do to unconventional ideas and what it costs when those systems win. The United States Air Force in 1975 was not populated by stupid people. General Pugh, who looked at the Have Blue briefing and said it was not serious, was not a fool. He was a decorated combat veteran with 30 years of expertise who was applying the correct standards of his profession to an idea that genuinely appeared to violate the physical constraints of those standards. The problem was not his intelligence. The problem was that the institutional incentive structure rewarded the correct application of existing knowledge and punished the pursuit of knowledge that did not yet exist. Every bureaucratic system optimizes for the reduction of error by the standards it already understands, which means every bureaucratic system is structurally resistant to the kind of leap that produces genuinely new standards. The Skunk Works survived this problem because Kelly Johnson had built it deliberately outside the normal institutional structure, with a small team, minimal documentation, direct access to decision-makers, and a culture that treated the word impossible as a provocation rather than a conclusion. The F-117 was not just a product of good engineering. It was a product of organizational architecture that protected good engineering from the institutional reflexes that would otherwise have killed it. This pattern appears throughout military and technological history with a consistency that should disturb anyone who works inside a large institution. The tank was considered a ridiculous waste of resources by most British Army generals in 1916. The aircraft carrier was considered an expensive distraction by most naval strategists in 1935. Penicillin sat undeveloped for 11 years after Fleming's initial discovery, because the institutional medical establishment could not allocate resources to something so speculative. In every case, the idea that changed everything was initially evaluated by people who were not wrong by the standards of what they already knew. They were wrong by the standards of what was about to become true. The only way to be right in those moments is to be willing to operate outside the institutional consensus before the consensus has any reason to change, which is the specific kind of courage that is almost never rewarded in advance and almost always vindicated in retrospect. Now, for the detail that most accounts of the F-117 program leave out the piece of the story that reframes the entire narrative in a way that even most aviation historians find striking. Pyotr Ufimtsev, the Soviet physicist whose 1962 paper made everything possible, was still alive when the Gulf War was fought. He was 70 years old, living in Moscow, aware that his work had been used by the Americans to build the aircraft he was watching on Soviet state television, the aircraft that was destroying Baghdad, while every radar system his country had built declared the sky empty. He had emigrated to the United States in 1991, year before the war, and was working as a researcher at the University of California in Los Angeles. He watched the Gulf War coverage from an apartment in California. The man whose equations had been dismissed by his own government as militarily useless, whose work had been handed to the American military establishment through the simple act of being left unclassified, was living as an American resident, while the weapon his mathematics had made possible was demonstrating in real time that the Soviet air defense doctrine he had grown up inside was permanently broken. He was later asked in an interview whether he felt any particular emotion watching the coverage of the air campaign. He said that he felt the same thing any physicist feels when a theoretical prediction is confirmed by experimental evidence: satisfaction at the precision of the result. He said nothing about the geopolitical implications and nothing about the country he had left. He was a man who thought in equations, and the equations had been correct. From a physics paper that a government threw away, written by a man his own country considered irrelevant to 42 aircraft that destroyed the military infrastructure of a nation in 43 days without a single loss. The F-117 program answers the question of where genuine revolutions come from. They do not come from the center of institutions. They come from the people working at the edges, reading papers nobody else reads, asking questions. The consensus has already answered, and refusing to accept that impossible is a permanent condition rather than a temporary failure of imagination. Dennis Overholser found an equation. He believed what it said. He built the math into a shape, the shape into an aircraft, and the aircraft into a new kind of warfare. And because he did that, and because Ben Rich protected that work against every institutional force that tried to stop it, the pilots who flew over Baghdad on January 17, 1991, flew home. Every single one of them. That is what the courage to be wrong by existing standards and right by future ones actually costs and actually buys. If this story reached you, share it with someone who still believes that the most dangerous words in any organization are, "We already know the answer."